We will now look at the binomial distribution in a different limit, in the limit where we have the probability p being small. Okay, so let's recall the binomial distribution. So let's consider, to start with, the binomial distribution. The binomial distribution is P of n, combinations of capital N objects taken n at a time, multiplied by P to the n, Q to the n minus, capital N minus n. Q is 1 minus P, remember. So it is 1 minus P. P plus Q is equal to 1. 1 minus P to capital N minus n. So when we have a large number of objects, capital N much greater than 1, the probability distribution turns into a smoothly varying function. The probability distribution can be approximated using the Gaussian distribution. This is what we have shown in the previous videos. And now we're going to investigate the limit. So let's say now we're going to investigate what happens if p is small, p is much less than 1, and we're looking at n much less than capital N. So we're looking at this limit. So if I look at the first term here, so this term, the first term, I have capital N factorial divided by capital N minus n factorial, and there's a 1 over n factorial here as well. So I'm just concentrating on this term. So this is going to be capital N minus 1, capital N minus 2, all the way up to capital N minus n plus 1. The next term is capital N minus n factorial, so that will cancel. And I ask myself, how many terms do I have here? The number of terms is, if you calculate, the last term is capital N, the first term is capital N minus n plus 1, divided by the increments of 1. So I have capital N minus n plus n minus 1, capital N minus n plus n minus 1 divided by 1. So this is going to be capital N minus 1, so I have to add 1 to it to get the number of terms. Last term minus the first term divided by number of increments plus 1 gives me the number of terms. So this is basically equal to n. So I have here n terms in this product. Okay, and I also know that n is much less than capital N. So if you look at the second term, capital N minus 1, it's approximately capital N. And if you look at the last term, capital N minus n plus 1, that is also approximately capital N. So I can say that capital N factorial divided by capital N minus n factorial is approximately equal to capital N multiplied by with itself n times. So capital N to the power n for n much less than capital N. And now basically this is going to tell me that I can replace this term with capital N to the power n divided by n factorial. Now I want to concentrate on this term, 1 minus p to the power capital N minus n. So for this one, I define y is equal to 1 minus p to the power capital N minus n. Then if you look at natural logarithm of y, it will be capital N minus n, natural logarithm of 1 minus p. And since I have capital N minus n approximately equal to capital N, n was chosen to be much less than capital N. So the first term here is going to be capital N. So this will be replaced by capital N here. And this will be replaced by what? So I have to figure that out. And natural logarithm of 1 minus p, in the limit p is much less than 1, which is what I am considering here, is in the Taylor series expansion, natural logarithm of 1 plus the derivative of natural logarithm of 1 minus p with respect to p minus evaluated at p is equal to 0, p minus 0, and higher order terms. So natural logarithm of 1 is 0, so this is 0 plus 1 over 1 minus p. The derivative of 1 minus p is minus p. This is the derivative of minus p is minus 1 multiplied by p. This is going to be evaluated at p is equal to 0 here. So I will have approximately, if I neglect the higher order terms, minus p. So that means I'm going to replace this term with minus p. So if I have natural logarithm of 1 minus p to be replaced by minus p, then basically I'm replacing for the natural logarithm of y, I have capital N times minus p. So it's going to be minus n p, and y will be replaced by e to the power minus n p. So what was y? Y was 1 minus p capital N minus n. So this is to be replaced by e to the power minus n p. So if I continue this, the probability distribution that I'm getting, p of n in this limit, when p is much less than 1, n is much less than capital N, is capital N to the power n divided by n factorial, p to the n, and then I have exponential to the power minus np. So this is np product to the power n, exponential minus np divided by n factorial. And if I define lambda to be capital NP, then this distribution will be given by lambda to the n divided by n factorial e to the minus lambda. So basically I have reached the end result here. This is known to be a Poisson distribution. and it works in the limit p is much less than 1 and n is much less than n. So this is the limit in which it works. Now I want to calculate the average value or mean value of n using the Poisson distribution to check the validity of this result. So let's start calculating the average value of n. So for n bar, I have to go through all possible values of n from 0 to capital N, multiply n with its probability distribution. So I'm assuming that the Poisson distribution applies in this limit. I have p is much less than 1, n is much less than capital N. So this is going to become summation from n equals 0 to capital N, n lambda to the power n over n factorial e to the minus lambda. Now this e to the minus lambda does not have an n term in it, so I can take it out of the summation. So this is e to the minus lambda summation from n equals 0 to capital N, lambda to the power n over n factorial multiplied by n. And this is going to have e to the minus lambda n equals 0 to capital N, lambda to the power n, n times n minus 1 factorial n. So these two n's will cancel. So therefore, for the mean value of n, I will have e to the minus lambda n equals 0 to capital N, lambda to the n divided by n minus 1 factorial. Now n equals 0 term basically vanishes here. So if you look at the original summation, if you put n equals 0 here, you will get a 0. And so I don't have to start counting from n equals 0. And the probability for n values will be negligibly small when I'm close to capital N. So we can take capital N to be infinite, to a good approximation. So with these two, basically this turns into the summation e to the minus lambda. The summation actually starts from 1, goes to infinity, lambda to the n divided by n minus 1 factorial. And now I'm going to call n minus 1 to be k, so that n is going to be k plus 1. So the average value or mean value of n will be e to the minus lambda. When n is equal to 1, k is equal to 0. So it starts from 0, goes to infinity. Lambda to the power k plus 1 divided by k factorial. So this is going to be lambda times e to the minus lambda, summation from 0 to infinity, lambda to k to the power k divided by k factorial. Now I'm wondering what this is. So if you consider the exponential function e to the x, that is its behavior for x much less than 1, it's going to be the Taylor series expansion e to the power 0 d dx e to the x evaluated at x equals 0 times x plus second derivative of e to the x evaluated at 0, x squared over 2 factorial, etc. So this is actually 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. So this summation basically k equals 0 to infinity lambda to the k divided by k factorial is actually representing the exponential function e to the lambda for lambda small. So this is approximately equal to e to the lambda for lambda small. So it has to be a small value of lambda. And then I have for the average value of n, lambda e to the minus lambda, e to the plus lambda. So these two will give me a 1, so that I will find the average value of n is lambda, and lambda is capital N P. So the mean value in the Poisson distribution is capital N times P, the same mean value that we obtain in the Gaussian distribution. Okay, so let's take a look at what we have done. We have considered the binomial distribution in a different limit, in the limit when the probability of one of the two possible outcomes is much less than 1, and the number n, the number of subsystems, or the number of outcomes that give us the a certain value for the outcome with the probability p should be much less than capital M. And anyway, the probability p is very small. So in this limit, the number of combinations term capital N factorial divided by capital N minus n factorial is approximately equal to capital N to the power n, because n is much less than capital N, and 1 minus p to the power capital N minus n, this term is basically equal to e to the minus np, or approximated to be e to the minus np, because capital N minus n can be replaced with capital N, and 1 minus p, if you consider this term natural logarithm, you can see that its behavior for p much less than 1 is minus p to first order approximation, so that the 1 minus p to capital N minus n becomes e to the minus np. So I have considered these two approximations here. When I plug them in, I see that capital N to the power n, p to the power n, e to the minus capital NP divided by n factorial is my distribution. And just to make things a little bit simpler, I have redefined capital NP to be lambda, so that the distribution has this form: lambda to the power n divided by n factorial e to the minus lambda. Poisson distribution, which works in the limit n much less than capital N, p much less than 1. Then we have shown that using the Poisson distribution, we calculate the mean value of n, and in this limit, the mean value of n we find to be capital NP by recognizing two things. One is that the summation does not have to start from 0, it can start from 1 because the 0 term vanishes. And two, the summation does not have to end at capital N, because we have this capital N number rather large. We can take it to be infinite for a good approximation in the summation. And there we recognize the Taylor series expansion of the exponential function around small values of the power in the exponential, and we show that the average value of n is lambda, which is capital NP, that is consistent with the um, Gaussian distribution calculation we have done before. So just to summarize things here, we have the binomial distribution, which is going to apply when you have a problem that has two possible outcomes. It's given by the combinations of capital N objects taken n at a time, p to the n, q to the capital N minus n, where p plus q is equal to 1. And in the limit where we have n close to its most probable value n tilde, which is far from 0 and capital N, and capital N is very large. So in this limit we can replace this binomial distribution with the Gaussian distribution, so it becomes 1 over square root 2 pi npq e to the power minus 1 over 2 n minus np divided by square root npq square. And in the limit p is much less than 1 and n is much less than capital N, the binomial distribution can be approximated to be lambda to the n over n factorial e to the minus lambda, where lambda is capital NP, the Poisson distribution. So here we have the most general one, the binomial distribution, for capital N very large and close to the mid values of n, we have and p should not be 0, q should not be 0 or close to 0. We have the Gaussian distribution, which we can use as a probability distribution function for because in this limit it's going to be a smoothly varying function. And then here we have the limit for p much less than 1 and n much less than capital N, the Poisson distribution limit.